Hello students, this is the third class of the lesson Electricity. In this class, we are going to learn resistivity of a conductor, combination of resistors in series and combination of resistors in parallel. Students, in the last class we discussed about the factors on which the resistance of a conductor depends. Can you recall those 4 factors? Yes, the resistance of a conductor depends on the length, the area of cross section, temperature and nature of the material. That's right. Come, let's start today's class with an activity. Children, see here, if I increase the length of the conductor, the resistance also increases. And if I reduce the length, see, the resistance also decreases. Thus, we can say that resistance of a conductor is directly proportional to its length. Also observe, if I increase the area of cross section, the resistance decreases, and if I reduce the area of cross section, the resistance increases. Thus, resistance of a conductor is inversely proportional to the area of cross section. We can then write, resistance of the conductor is directly proportional to its length and inversely proportional to its area of cross section. That is, R is directly proportional to L and R is inversely proportional to A. That is, R is proportional to 1 by A. By combining these two relations, we can write R is proportional to L by A. R is equal to rho into L by A, where rho is the constant of proportionality and is called the electrical resistivity. It is a characteristic property of the material. SI unit of resistivity is ohm meter. Both the resistance and resistivity of a material vary with temperature. Children, the metals and alloys have very low resistivity in the range of 10 to the power minus 8 ohm meter to 10 to the power minus 6 ohm meter. So, they are good conductors of electricity. Insulators like rubber and glass have very high resistivity of the order of 10 to the power 12 to 10 to the power 17 ohm meter. Resistivity of an alloy is generally higher than that of its constituent metals. And alloys do not oxidize readily at high temperatures. For this reason, they are commonly used in electrical heating devices like electric iron, toasters, etc. Now let's see the resistivity of some common materials. This table shows electrical resistivity of some substances at 20 degrees Celsius. Here we can see that good conductors have very low resistivity and alloys, they have comparatively higher resistivity than the metals, and insulators, they have very high resistivity. Nichrome, which is an alloy of nickel, chromium, manganese and iron, is commonly used in electric iron because of its high resistivity. The resistivity of nichrome is 100 into 10 to the power minus 6 ohm meter. Then tungsten, it has a resistivity of 5.2 into 10 to the power minus 8 ohm meter, which is comparatively higher than copper and aluminium. Also, it has very high melting point. So, it is used almost exclusively for filaments of electric bulbs. Then we know copper and aluminium are generally used for electrical transmission lines because they are very good conductors as their resistivity is very less. Students, in various electrical gadgets, we often use resistors in various combinations. Now let's see how Ohm's law can be applied to this combination of resistors. There are two methods of joining the resistors together. This figure shows an electric circuit in which three resistors having resistance R1, R2 and R3 are joined end to end. Here the resistors are said to be connected in series. See the second figure. In this electric circuit, the two terminals of three resistors are connected to the same two nodes X and Y. Here the resistors are said to be connected in parallel. See these pictures. Here the bulbs are joined end to end and they are in series. Here the two terminals of the bulbs are connected to the same nodes and these bulbs are said to be connected in parallel. Students, what happens when two or more resistors are connected in series and when they are connected in parallel? Will there be any change in the value of current through the circuit? What will be the total resistance then? Come, let's try to understand all this through an activity. See, here I have connected three resistors in series. I have also connected an ammeter and voltmeter to measure the current and potential difference respectively. See the total current through the circuit. It is 0.4 ampere. Let's take it as I and write here. Now let me use this portable ammeter and check the current between the resistors. Let me write these values as I1, I2 and I3. We find that value of current is same in every part of the circuit. That is I1 is equal to 0.4, I2 is equal to 0.4 ampere and I3 is also equal to 0.4 ampere. That means the same current flows through each resistor. Now note the voltmeter reading, that is potential difference across these two ends, and take it as V. It is 9 volt here. Now measure the potential difference across the first resistor. Let it be V1. So here V1 is equal to 3 volts. Potential difference across second resistor, that is V2 is equal to 3.2 volts. And potential difference across the third resistor, V3 is equal to 2.8 volts. We find that all four values are different here. Let's try to deduce a relationship between V, V1, V2 and V3. What do you see from these values? What is the relationship between this total potential difference and potential difference across individual resistors? Yes, if you observe, you will find that equivalent potential difference V is equal to the sum of the potential difference across individual resistors. That is, total potential difference here is equal to the sum of the potential difference across the individual resistors. You can find C3 plus 3.2 plus 2.8 is equal to 9 volt. That is, V is equal to V1 plus V2 plus V3. By Ohm's law, we have V is equal to IR. So V1 becomes IR1, V2 becomes IR2 and V3 becomes IR3. If we substitute it here, we'll get IR is equal to IR1 plus IR2 plus IR3. That is, IR is equal to, I is common here, so we can take it out, and then R1 plus R2 and plus R3 will remain inside the bracket. So I in the LHS and I in the RHS will get cancelled, and we are left with R is equal to R1 plus R2 plus R3. Since the resistors are connected in series, we can write the equivalent resistance as Rs, that is equal to R1 plus R2 plus R3. By this we can conclude that when several resistors are joined in series, the resistance of the combination Rs is the sum of all three individual resistances, and thus it will be greater than any individual resistance. Now, let's consider three resistors joined in parallel. First, let's note the ammeter reading and write it as I. It is 2.72 ampere. Then, let's measure the current through R1, R2 and R3 and write the values as I1, I2 and I3. So, I1 is equal to 0.82 ampere, I2 is equal to 0.9 ampere and I3 is equal to 1 ampere. Now, let's note down the potential difference V across these 2 points. It is 9 volt. Let me measure the potential difference across each resistor now and write them down as V1, V2 and V3. Here we can see the potential difference across R1, that is V1 is equal to 9 volt, and potential difference across R2, that is V2 is equal to 9 volt again, and potential difference across R3, that is V3 is equal to again 9 volt. So, we find that potential difference across each resistor is same as that of V. V1 is equal to V2 is equal to V3 is equal to V. But I is not same. See here, I is different from I1, I2 and I3. Can we deduce the relationship between these 4 values? Yes. If you observe, you will find that total current I is equal to the sum of individual currents through each branch of the combination. If we add 0.82, 0.9 and 1 ampere, we will get 2.72 ampere. That is, total current through the circuit is equal to the sum of the individual currents through each branch. We can write it as I is equal to I1 plus I2 plus I3. By Ohm's law, we have I is equal to V by R. So, we can write I is equal to V by R and I1 is equal to V by R1, I2 is equal to V by R2 and I3 is equal to V by R3. So, V is common here. If we take it out and write, V in the LHS and V in the RHS will get cancelled and we will be left with 1 by R is equal to 1 by R1 plus 1 by R2 plus 1 by R3. As it is a parallel combination, we can write the equivalent resistance R as Rp. By this relation, we can conclude that when several resistors are joined in parallel, the reciprocal of the equivalent resistance is equal to the sum of the reciprocals of the individual resistances. That is, 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3. And you will find that in parallel combination, equivalent resistance Rp is less than any individual resistance. Okay children, now let's see how the series and parallel combinations are used practically. There are some advantages of parallel combination over series combination. Come, let's see them. See these pictures? Here the two bulbs are connected in series. Can you think what happens if one bulb or one component fails in this circuit? Also see this figure. Here the two bulbs are connected in parallel and you can see what happens if one bulb or one component fails. Here we can see that in series circuit, when one component fails, the circuit is broken and none of the component works. But in parallel, it does not happen like that. If one component fails, it will not affect the next one. Then we know that different appliances have different requirement of current. This cannot be satisfied in series as current remains the same. We have seen that in a series circuit, the current is constant throughout the electric circuit. Thus, it is obviously impracticable to connect an electric bulb and an electric heater in series because they need currents of widely different values to operate properly. And we know that the total resistance in a parallel circuit is decreased. This is helpful particularly when each gadget has different resistance and requires different current to operate properly. Okay students, that's all for today. As usual, here are some questions. Answer them and check your understanding of today's class.
To watch more such videos, please subscribe my channel.